Okay, so we're going to continue on from what we did yesterday. So yesterday we talked about trigonometric integrals. Like it was a lot of U substitution basically. So we're going to continue in a similar vein to that. So let me bring this up to writing mode. There we go. So we're going to talk about something called trigonometric substitution. So it involves... Oh my god, where's my keyboard? Shh. So what this involves integrals that don't look like they're trig integrals, but actually are. Okay, so let's start off with a nice example. Let's look at the integral of the square root of 9 minus x squared dx. So you look at this and you're like, yeah, this is obviously not a trig integral. Like it has a square root of 9 minus x squared. And actually there's a good reason to think or feel that this actually is a trig integral. Any ideas why? Well, yes, but we're not going to just like write with the answers. So looking at this on its face, there's actually a good reason to believe that this will involve trigonometric functions. Any ideas as to why? I'm not asking you what the antiderivative is. I mean, I'm saying, looking at this, why should your spidey sense be like, actually, yes, I am expecting this to involve a trig, something having to do with trig? Yes, but like even more basic than that, because like that would require that you'd actually know something about those trig identities and stuff. So like, let's look at the function we're dealing with here. Oops, what the hell? There we go. My function is the square root of 9 minus x squared, which I could write as y equals square root of 9 minus x squared. Does anyone know what shape this has? It's shaped like a circle, and yeah, it's a semicircle actually. And what should circles make you think of? Like what a... Yeah, well, right. But the unit circle, yeah. So circles make you think of the unit circle, and then what do you use the unit circle for? Trig stuff, right? Yeah, does that make more sense? Why I'm like, all those things that you're saying, yes, technically true, but like, you don't even need to know like all this stuff about arc sine and stuff. Because like if you look at this, if you square both sides of this thing right here, right, you're gonna get y squared equals 9 minus x squared. And if you bring that x squared over, you'll get x squared plus y squared equals 9. So we know that this thing is just a circle of radius 3. Well, semicircle of radius 3. Okay, right? So this is your f of x equals square root of 9 minus x squared. So even though it doesn't look like it, you have some immediate reason to suspect that trig stuff might be involved. Does that make sense why I'm saying that? Like, if you pause for a moment and like activate your knowledge, it's not a far reach to say like, oh, well, I'm dealing with a circle, so yeah, trig stuff might end up being involved. Okay, so let's talk about like why it does end up getting involved. Let's draw a triangle. Okay, that was a horrible triangle. I'm gonna do that over. Okay, it doesn't want to let me erase. Come on, there we go. I want to draw those like as nice straight things. Okay, I don't want it to be white. I want it to be that cool green color. There we go. Sorry, I just want my triangle to be beautiful. Okay, why does it not want me to... There we go. Come on, beautiful triangle. There we go. Nice. Okay, now I've got a beautiful triangle. Okay, so let's say that your theta is right here. So, if I told you that the sine of theta is equal to x over a, then what do you need to do? What can you say about this triangle over here? Well, it already is a right triangle, but I'm saying if sine of theta equals x over a, like, what can you do? Awesome. And what else? Awesome, thank you. Which means you could solve for this base right here. We know that the base squared plus x squared equals a squared by the Pythagorean theorem, which would mean that the base squared equals a squared minus x squared, which means what is the base equal to? The square root of a squared minus x squared. Okay, what the hell? Let's put that down. We know that the base equals the square root of a squared minus x squared. And you look at this, and you're like, ooh, my spidey sense is tingling because this actually looks like this over here. Does it not? Right? Okay. So you have to remember that, like, when you're doing math, like, you have to, part of this is creativity, and creativity comes from noticing things and having the faith in yourself to explore where that shit goes and not just like throw out like solutions that are like keywords, like, right? You gotta like write down and like puzzle through the stuff. So it's sort of interesting because you might now realize that to solve this problem, maybe we can say that the sine of theta equals x over 3. And then you can draw a triangle. And we get x. And we get 3. Which means down here on the base, you have 9 minus x squared. And you're like, oh shit. That's what I've got right there. Right? Right, remember our original integral is integral of the square root of 9 minus x squared? So this thing that you're integrating, it has something to do with the base of this triangle. And now we can see the connection to trig functions. Well, we know that the sine of some angle equals x over 3. Okay. Mucho bueno so far? Okay, now, this allows you to make a substitution, because you have an equation. If I multiply both sides by 3, the 3 times the sine of theta is equal to x. And now I can take my original integral. Actually, well, let's back up a little. So if 3 sine theta equals x, if you take the derivative with this, ooh, 1 second, I have to turn off my stove. So, if you take the derivative of both sides, no, I don't want to say that. So if x equals 3 sine theta, let's calculate the differential. There we go. Then what is dx equal to? Dx is going to be equal to 3. What's the derivative of sine? Yeah, d theta. Okay, so the way you calculate the differential, like, I mean, hopefully you remember how to do that. You learned that at the end of 101A. Okay, so now we can make some substitutions. My square root of 9 minus x squared dx is equal to square root 9 minus, now my x is equal to 3 sine theta, oops, and that is being squared. And what can I replace my dx with? I can replace my dx with 3 cosine theta d theta. So this is like a tricky substitution, because we realize that that 9 minus x squared, that's like part of this triangle, right? And that it's only part of that triangle if the sine of theta equals x over 3. Which then allows us to say that 3 sine theta equals x, right? This is sort of like a u substitution, right? But instead of using the variable u, I'm now replacing with the variable theta. Okay, so let's simplify this. So you're gonna get the antiderivative of the square root of 9 minus 9 sine squared theta. Let's take that 3 out. Cosine theta d theta. And actually, what can I change inside the square root? So what can I do inside the square root? So looking at inside the square root, what can I do? Sure, but there's actually something easier you can do. Thank you. Square root of 9 is 3. Okay, now what can you do with this 1 minus sine squared? Yes. What can you do now with the 1 minus sine squared? Yeah, and then you're like, oh wow, this was like fated. Because you see how the square root and the square cancel? So you get 3 cosine theta. Which means you now have 3 times the antiderivative of the square root of 9 minus 9 squared theta becomes 3 cosine theta. Girls, close your door! Okay, 1 second.
You don't know. God is lying to you. God is lying to you.
Silence. back. Okay, so you have that replacement there, and then what do you're left with the cosine theta from this, d theta. Which means, what are you ending up with? You can take the other 3 out and you get 9 square root cosine squared theta d theta. And then now we learned how to solve this last time. Right? Does that make sense? Like, do you see how what we've done is we've successfully taken something which did not look like a trig integral, and then what do we have now? A trig integral. Okay, 1 second. I'm having technical difficulties. I want to type over here. There we go. We now have a trig integral. So what did I do last time when we had like cosine squares to deal with? What was my method of dealing with them? Do we remember from yesterday? Not use substitution. It was not integration by parts, although we did use those things. I'm saying for this one in particular, because, like, look, we have a cosine squared. We can't let u equals cosine squared. Let's just, like, walk through this. So if u equals cosine, then what will my du be equal to? Let's just finish it so people can see. If my u equals cosine, what will my du be equal to? Negative sign. Do you have a sign anywhere? No. So that's not going to work, right? Okay. So there's something else we did, especially when we had powers, even powers of cosines. I'm going to start writing and we'll see if people can recognize it. Not converting to a power of sine. What is this called? There's a name for it. I talked about it last time. The power reduction formula. Yeah, whenever you have like powers of cosine like this and you don't have like a matching power of sine, you're not going to be able to do u substitution. You should use the power reduction formula. So you get 9 integral 1/2 plus 1/2 cosine 2 theta d theta. And now you can do a u substitution. Your u will be equal to 2 theta, which means your du is going to be equal to 2 d theta, which means 1/2 du equals d theta. So you can get integral 9, you're going to get 9 antiderivative of 1/2 d theta plus 1/2 integral cosine 2 theta d theta. So you're going to get 9/2 theta. Okay, now let's work through this. You're going to get 1/2 integral cosine u, and then what's d theta equal to? 1/2 du. Okay, and now you can integrate that. You get 9/2 theta plus, the 1/2 will come out, you'll get a 1/4. And then what's the antiderivative of cosine u? Why, it's sine u. So if you go back to it in terms of theta, you're going to get sine of 2 theta. So your antiderivative for our trig integral is 9/2 theta plus 1/4 sine 2 theta. Or wait. Yeah. Okay, and we're not done yet because my original integral, what was the variable? Like if you go back to the original problem, what was my variable? It was this integral of square root of 9 minus x squared dx, right? That's in terms of x's, right? That was the original problem. Now we have an antiderivative in terms of theta. So what do I need to do? I need to substitute back to x's to get my proper answer. But before we do that, I'm going to put 9/2 theta plus 1/4. Do you remember the double angle formulas? What is sine of 2 theta equal to? It's equal to 2 sine of theta cosine theta. Okay, now, what was the original substitution that I made to get to my thetas? No, wait. No. This is not the original substitution. Like the actual original substitution. Wait 1 second. Someone's calling me. Hello? Oh my god, it's just one of those.
Congratulations, you won a Marriott hotel thing.
Okay. So what was my original substitution? This is not the OG substitution. To go from x to theta, what was my original substitution? Yes, thank you. 3 sine theta equals x. Which means, what is sine theta equal to? X over 3. So wherever I see a sine theta, what can I replace it with? An x over 3. So we're going to make some changes here. That 1/4 and the 2 will give me 1/2. My sine theta is now x over 3. Okay, making sense so far? Now, I can replace this theta right here by taking the sine inverse of this equation right here. If you take the sine inverse of both sides, you get theta equals the sine inverse of x over 3. So I'm going to get 9/2 times sine inverse of x over 3. Okay, now what's the last replacement that I need to make? Or what's the thing that I need to replace? There's one more thing that I need to replace. Yes, the cosine theta. And to do this, you need to remember that we started off with a triangle. This is theta. Okay, we have a x over here, a 3 over here, and a square root of 9 minus x squared right here. What is cosine of theta equal to? No, that's the sine of theta. There we go. Nice. It's okay. I appreciated the original enthusiasm, but yes, it was wrong. Boom! You now have your antiderivative in terms of x's. This is what you get when you integrate 9 minus x squared dx. And people were saying it earlier, like, oh, your answer is going to have a sine inverse. Well, now you see why it has a sine inverse. Why? Because you get that theta there, right? And theta is the sine inverse of x over 3. Plus all this other crap. So I'm going to pause. There was a lot to this. No, I'm sorry. Yeah, I know it's a lot. Sometimes when you learn this stuff, it has this thing where, okay, so it's like doing math elegantly, like there's a lot of steps here, right? Do you see how like doing this problem like involved recognizing you were dealing with a semicircle and then recognizing that you can set up this triangle to make these substitutions? And then you needed to remember like all of these trig identities, right, to pull this off. Like it's a lot of pieces, right? And usually the problem is that most of the time and when you take pre-calc and you learn these identities, you're probably like, I mean, who gives a shit about this, right? Like, I mean, just be honest, like even a lot of teachers are like, oh my god, this stuff is so stupid, like you're never gonna use it. And then like here we are, right? And everyone's now like, oh man, I wish I just knew these trig identities so that like, you know, like life would be easier. Do you know what I mean by that? Like it's so many different pieces coming together. And now is probably not like the greatest time in the world to do this because like everyone's like stressed out and COVID and like, you know, you've been locked in your little cell for the last like year, right? Having to do math. So, you know, part of it is just also having like the patience with yourself to know that like there's just a lot of this stuff going on. I mean, there's a lot of things, right? And the only way you get good at this is by practicing with it, right? So like part of like lecturing is just like seeing me go through this, right? There's like a lot of different pieces. You're gonna have to go over it and then like integrate that knowledge. Alright. Let's do another one. Let's look at the integral of square root of 4 minus x squared all over x dx. Let's write an example. 1 second. Okay, I'm back. So, okay, looking at this, hopefully you recognize that this part up here is your a squared minus x squared. And you're like, okay, I'm going to set up a triangle. Okay, so this right here is your 4 minus x squared, which means that you have this height, which will be 2, and this hypotenuse, which will be x. Which means you get a variety of substitutions that you will be able to make. We know that the sine of theta equals 2 over x. Wait, yeah, yes. Wait. I fucked up. Erase. I want to change how I set this up. Let's switch the x and the 2. I want x here. I want 2 there. Thank you. So sine of theta will be x over 2. Which means what is cosine theta going to be equal to? The square root of 4 minus x squared over 2. And, I don't know, possibly you might have to use tangents. Let's just write it down. X over the square root of 4 minus x squared. So they're just there, right? Hanging out. We might use these facts later to do some substitutions. Yeah. Yeah. Yes. Okay, so what we need to do, remember your goal here is to turn this thing into something that's a trig integral. Okay, so I need to get rid of my x's. I need to get rid of my x's. That's hilarious. I made a funny. So I'm going to look at this sine theta equals x over 2, and I'm going to realize, what is x equal to? 2 sine theta, which means my dx is equal to 2 cosine theta d theta. And I make those appropriate changes. My new integral is going to be the square root of 4 minus 2 sine theta squared, all divided by x, which is equal to 2 sine theta, multiplied by dx, which is 2 cosine theta d theta. Okay, and so then you go to town, like, simplifying stuff. So you notice that inside of the square root, let's just do the work right here, you're going to get 4 minus 4 sine squared theta, which means when I take out those 4's, I'm going to end up with a 2, right? When I factor out the 4, I'm going to get 4 times 1 minus sine squared theta. So then we recognize that this is going to be 4 times cosine squared theta, right? That's inside the square root, right? So when you take the square root of that, the square root of 4 is going to give you 2. And then what's the square root of cosine squared? Cosine theta. Okay, so does everyone see what I did there? I just simplified inside of the square root. And then I took the square root of what I got at the end. Hopefully. And then what is that being divided by? 2 sine theta. And then what are we going to multiply that by? 2 cosine theta d theta. And then you're like, oh, okay, cool, those 2's are gonna cancel. And I could factor out that one leftover 2 to be put in front of everything. So what am I left with? A cosine squared divided by a sine theta d theta. Okay, so now we're looking at this, and there's several things that I can turn it into, but I think I'm going to write this as cosine theta over sine theta times cosine theta. Ooh, wait. Okay, and so the cosine theta, sine theta is cotangent times cosine. Is that going to work? Yeah, I think this will work. I think we can do a U substitution though. So I'm going to rewrite this. I'm going to break it up into pieces. I've got my cosine theta. I've got my sine theta. It's multiplied by cosine theta d theta. Okay, and let's see if we can do some U substitution to make our lives a little easier. I think this will work. I'm going to set my U equal to sine. So if U is equal to sine theta, what's my du equal to? So if my U is sine, what's my du going to be? No, not theta. Minus cosine theta, right? Minus cosine theta d theta. Which means I can move that minus over, and I can get minus du equals cosine theta d theta. And that part is right there. Yeah, the stupid minuses is really annoying. Okay, so that part's right there. And then my sine theta I can replace with u. And now I just need to figure out what to do with my cosine theta. Oh, damn. Okay, wait. So I've got u equals sine theta, yeah. Okay, then I've got my du is cosine theta d theta. Crap, I think I need to rearrange this a little. We're so close. Okay, I'm gonna leave that there. Okay, wait. I think I know what we need to do. Okay, cosine squared, that cosine squared on the top, I'm going to rewrite it as 1 minus sine squared. Okay, don't write this down yet because it might change. Does that make sense? Just pause for a moment. Okay, now I can break this up into 2 of them. I can get the integral, so it's 2 times bracket, integral 1 over sine theta d theta minus the integral, and then you get sine squared over sine. Wait, what the hell? Okay, yeah. There we go. Okay, cool. So I'm good so far. Okay, this one right here, you can find the antiderivative. What is the antiderivative of sine theta d theta? I'm just gonna get cosine theta, right? Wait. Man. I feel it. My brain is buckling under the stress. What is the antiderivative of sine theta? What has a derivative equal to sine minus cosine, right? Yeah. Boom. But then the other one, I'm not getting the other one. Okay, the other one's a little tricky. Okay, so I've got that piece. Okay, and those two minuses are gonna cancel out to be plus cosine theta. Okay, now we've got to get this one. Okay, so I've got one piece of it. Now I've got to get the other piece. How should I integrate 1 over sine theta d theta? Damn. Just put this over here. Okay, that's what we're working on, this piece right here. We already got the one on the right. Well, maybe we rewrite it, that will help. 1 over sine is cosecant. Does anyone know anything that has a derivative equal to cosecant? Yeah, let's write them down. The derivative of sine equals cosine. Cotangent is minus... Yeah, the derivative... Okay, yeah. So, because you know that the derivative of tangent equals secant squared, and the derivative of cotangent is minus cosecant squared. But we want something that ends up with cosecant over here. What is the derivative of... Oh, damn. Let's look at... Okay, I'm gonna like stoop low and I'm just gonna look up on the internet to see if there is a solution for this, because I don't think I'm gonna come up with it on my own table of integrals. Let's see. I'm gonna share my screen. Sometimes you just need to admit defeat. Oh, Reddit has us. Okay, what is it that we want? We're integrating cosecant. Oh, look! Number 19! We're integrating cosecant. There's our answer. Oh my god, that's sort of funny. We're integrating cosecant. Reddit had it for us. Apparently the antiderivative of cosecant is going to be the natural log of cosecant theta minus cotangent theta, which, oh wow, I don't think I would have come up with that. Okay, which means we're going to get 2 natural log of cosecant theta minus cotangent theta, and then plus that cosine theta that we had started with. The one on the right. So this is my antiderivative with thetas. Okay, but now I gotta substitute everything back in, right? So we need to replace several things. This cosecant theta, the cotangent theta, and the cosine theta. Okay, so our original thing was that sine of theta was x over 2, right? And what was my cosine of theta equal to? It was x... Oh shit, what was it? Scroll up. I don't remember. Cosine of theta was square root of 4 minus x squared over 2. So cosine of theta is the square root of 4 minus x squared over 2. And then I had written this down. Tangent of theta is equal to... Let's go back up and look. X over the square root of 4 minus x squared. So now we can start making some replacements. Okay, so I need to replace cosecant theta. Cosecant is 1 over sine, right? So if sine is x over 2, what is cosecant theta equal to? 2 over x. So you get the natural log of 2 over x minus cotangent theta. Well, if tangent theta equals x over square root of 4 minus x squared, then cotangent theta will be equal to the square root of 4 minus x squared over x. Plus cosine theta, and cosine theta we had written over there was the square root of 4 minus x squared over 2. And then don't forget to put plus c. That is what you get when you integrate the square root of 4 minus x squared over x dx. Boom! There's my antiderivative. Holy crap, that was actually hard. That was legit hard at the end there. Just look at how horrible these antiderivatives look. Does everyone agree with me that they're just like straight up complicated looking? Like there's a lot to them. Yeah. Yes, that is a very nice way to say that. Yes, the homework will be fun. The homework will be very fun. Actually, to be honest, the way you end up skipping this in real life is you just solve it numerically. You just basically say like, well, finding the formula, let's just get the number. But stuff like this shows up a lot in physics. Because like usually you have like some sort of thing that's like oscillating, and that like involves like trig functions. It also shows up a lot like in electrical engineering. So usually, yeah, I feel bad for engineers and physicists because like you actually have to do this. Does that sort of make sense? Like sometimes it's like, oh my god, like literally the only way to answer this is to like to solve this horrible integral. And then you're like, okay, there we go. We got our answer. Awesome. It is really horrible. So, just to give you an idea, like, all of these problems work like this. You're going to notice, a lot of the time, the giveaway is that you're going to have the square root of a squared minus x squared, and usually you're going to have, like, some sine theta, like, equals, like, so basically you're going to have sine theta equals x over a. That's, like, the substitution that you're going to have to make most of the time. Okay, the other common thing that you encounter is this, and that usually involves that you're going to use tangent. And if you go and you like draw everything, you'd see that that's basically what's going to happen, because you're going to get tangent equals x over a. And then what do you have to do? You just draw the triangle. You get rid of your x's with these substitutions, right? You're going to get, like, in this case, like a sine theta equals x. Or on the one below, you're going to get a tangent theta equals x. And then you start getting rid of all those x's, you replace them with thetas, you get yourself a trigonometric integral, and then you integrate that using the stuff that we learned last time. And then you get your antiderivative, but your antiderivative has all these thetas, and then you have to, like, resubstitute all the stuff back in, right? So, like, the substitution you're going to end up making to fix the problem that you created is the fact that theta equals the sine inverse of x over a, or you're going to have, like, theta equals the tan inverse of x over a, right? That's how you get rid of your thetas, right? So you're going to integrate your trig valued function. You're going to have something with thetas, and then you need to get rid of your thetas. You're going to replace them with trig inverses. Or you're going to, like, look at, you know, this sort of stuff and realize, like, oh, that's just the cosine of something, or something like that. Okay. I think this is where we're gonna end today. I think we're done, right? Are we literally finishing on time? Yeah, we're just finishing on time.